screen. Yeah. Sorry.
No.
Yeah. Try this.
Okay.
This side. It's a little better. Yeah. It's a little better. Okay. Sorry for this technical issue. Thanks for coming to today's SER seminar. Today we have speaker Dr. Jianqiang Cheng from University of Arizona, System Industry Engineering Department. He got his PhD from University of Paris, and then he joined Sandia National Lab for 2 years to do the postdoc position. And his area is basically in stochastic programming, chance-constraint programming, and recently in the distributionally robust optimization. And he will be talking about computationally efficient approximations for distributionally robust optimization today. Great.
Okay. Thanks for the introduction. And it's my great pleasure to present some of my recent work here at George Mason University in this department. Right? I think your department is engineering management and operation research, right?
Systems.
Sorry.
So we do not have an engineering management degree.
Okay, my bad. Sorry.
Yeah,
and this work is joined with my PhD students and Mason Sharabi and my colleague, Jianqiang. Actually, right now he's faculty at the University of Michigan. So, first of all, I would like to outline my talk today. So first, at the beginning, we'll give a brief introduction about distribution robust optimization. Then we will present two approximations. One is outer, the other is inner. That means each of them, give a lower bound and upper bound respectively. Then we consider more general sum ambiguity set for DRO. After that, we numerically to show the performance of our proposed approach. And at the end, I summarize our talk. So here is a very general deterministic optimization problem. We have an objective function, fs, to minimize and subject to some cap X feasible region. So I want to remind you, actually, in this model, in this optimization problem, there is a strong assumption. What that? Is all the parameters involved are deterministic. Okay, that's the deterministic optimization problem. So, but we know, in practice or in real life, this is not true because every model, involves some degree of uncertainty. For instance, traditionally people, for instance, in terms of GPS, traditional GPS, more focus on the find a shortest distance from A to B. But nowadays, people are probably more interested, find a path from A to B with the least traffic time. But traffic time, that's not deterministic, At a different time, a different day, you have different, traffic. So that's the reason in this background, we should consider some uncertain parameter we call C here. So to simplify our introduction, we only consider uncertainty in the objective. Actually, all approaches we propose can also extend to the uncertainty in constraints. But just to simplify, the introduction of our main research. So here, C just represents some uncertainty. Okay, so question is, for this model, it makes no sense, Because for the different realizations, you have different objective function. So you don't know how to optimize. So the question is how to deal with this uncertain objective function. One way is robust optimization. What's a robust optimization? That means among all possible realizations, you consider the worst case, the worst objective function. This is robust. The good thing is this model is extremely robust because it either considers all possible realizations, And the bad thing is the solution is too conservative. Think about that. If you could see, is a normal distributed. That means, the positive infinity is one of the possible realization. Then the cost probably become positive infinity. That's too conservative. Then second one is called stochastic optimization. Stochastic optimization is just consider expectation of the objective function. That means if you know the information about f, right, then you can calculate expectation. The good thing about this model is what? If you are interested in the right long-term performance, long-term average of performance, then this is good model. But the bad thing is what? You need the right exact information about distribution f, so that right you can calculate the expectation. So each in the previous two models, each of them have the good thing and bad thing, good side and bad side, right? So next we want to present a trade-off model. It's called distribution bus optimization. That means in this model, you don't know the exact distribution f, but you know it belongs to some family of distributions. Distribution family, okay, we call it ambiguity set. Then in the same spirit of robust optimization, we consider the worst case distribution in that family. So that's the distribution robust. So for this model, why we call it a trade-off model? Because if the distribution family D or ambiguity set D only accounts for the support information, that means you only know the support of distribution F, then it becomes traditional robust optimization. And also the second case, if the D is a singleton, that means there is only one distribution in D, then it becomes the stochastic optimization. So that means this is actually the trade-off model, right? There are a lot of flexibility in the modeling. So from this, we can see, right, the ambiguity set D or distribution family D, right, is very important for DRO. So how to create a D? That's the question, right? Okay, most of the research in the DRO just consider two types of ambiguity set. One is a moment-based ambiguity set. That means you know the information about moments. For instance, you know the mean, that's the first moment, right? You know the covariance, that's the second moment information, right? And the second type of ambiguity set is called metric-based ambiguity set. What's that? That means if you have some reference distribution, for instance, you can use you sample to estimate a distribution. Then around that one, you consider all the distribution with some distance around the reference distribution. Okay, so how to calculate the distance between two distributions? They have different matrices, right? One is called KL divergence, also belong to the phi divergence. And the second type, okay, now the more popular one is the Wasserstein distance. So the difference between the two is if you consider KL divergence, if the nominal distribution is discrete, then all the distribution family, all distribution in that family now are also discrete. That's very restrictive. But if you use the Wasserstein distance, then you don't have that kind of drawback. Okay, so that's the reason why Wasserstein distance, right, nowadays are more popular. So, but in my talk, we mainly focus on moment-based ambiguity. Also, we will extend this result to the Wasserstein distance as well. Okay, so before I present the idea of my approach, I would like to use this numerical example, numerical result to show the motivation of my talk. For instance, this is a multi-product user vendor problem. Condition, multi-product user vendor problem. Then, if we use a DRO problem to consider DRO model, then if you want to solve the exact problem, unfortunately, it's not doable for our own personal PC. Okay, it's not doable. But if you use our proposal, right, to approximate outer and inner, that means we get lower bound and upper bound. You can see, for instance, for this size 700 the size, that means you have 700 different products within 220 seconds. We can with the ultimate gap bound actually with lost some ultimate gap within 2%. The second one, right, we also provide an outbound, right, in the approximation, you can see we solve the problem within 40 seconds, but with loss, right? With loss of the optimality within 2%. I want to show this is the motivation, right? You want to solve directly the exact problem. Unfortunately, we cannot do that. But why not? We take a step back to get some approximation, but with a high quantity. How we can do that? That's our next part. So first of all, I would like to talk about auto approximation. But before that, I would like introduce the ambiguity set we consider here. Sorry, I use this one. It seems that the pointer doesn't work. This one does. So we are in this moment-based ambiguity set. Actually, it comes three types of information. First, it has it has support information. Then you have the second one means the mean is belong to our ellipsoid centered at mu. For the mu, you can consider as a sample average or something else, right? It's a reference mean. And this is the second one means all the mean, right? The mean is the center, is belong to the ellipsoid centered at mu. And the third one means the covariance of the cosine is outbounded by gamma 2 sigma. And the sigma, of course, you can consider as a reference, right? Covariance. So corresponding, we have this DRO. We denote the optimal value by this stuff. Okay? So how to solve this problem efficiently? Before that, we want to do one-to-one mapping. Yeah, I can combine these two. Okay. Before that, I want to also mention we want to simplify, right? The idea of a proposed approach. We consider two simple cases about this support and the objective function. In this case, the support we assume just a polyhedron support, and also in terms of cost function fx cosine, we just assume is a piecewise linear. Okay. So with this, then we do one-to-one mapping. So, this is our original uncertain parameter cosine. Then we do this, linear transformation. So it means it's represented as a linear combination of the cosine I plus mu. So what's the cosine I? If cosine I, actually we have this corresponding ambiguity set, and here U is a matrix consists of eigenvectors, and then lambda is a diagonal matrix, and all the diagonal elements are eigenvalues. Okay, because sigma here we assume is a full rank. Actually, then you can see here is a one-to-one mapping. That means you lose nothing. Here, for example, cosine is n-dimensional. Here, cosine I is still n-dimensional. If you have a cosine, then you can find a corresponding cosine I. Also, if you have a cosine I, you can find a corresponding cosine. They are one-to-one mapping. Okay, based on this, we can get a corresponding ambiguity set for cosine I. Then, also, we want to introduce our idea. Without loss of generality, we assume the elements in number, actually the eigenvalue, are arranged in decreasing order. That means the first element, the one is greater than or equal to the second element in lambda. We assume decreasing order. That is a loss of generality. Okay, so with this one-to-one mapping, then the original DRO problem is equivalent to this DRO. Okay, so questions. We right now our focus is on this new DRO problem. So how to solve this problem efficiently? So in statistics,
can you repeat what were the assumptions that you made on function f?
Function?
Previous slide, you had some
Okay.
assumption about that. right?
But F, we just assume this three type of information.
So F is piecewise linear.
Oh, you mean objective function F? Yes.
Yes, yes.
Piecewise linear. Yes.
Piecewise linear and psi.
Yeah,
Okay.
in cosine. Yeah, and YK. Yeah, sorry. YK 0sy and YKS are affine function in
Sure.
X.
So you're approximating any function via a set of
Yeah, piecewise there.
Okay.
And you can see still the idea we present, right? Actually, regardless of the structure of F. Because we just use if for this point, we know the specific structure of the Fx cosine, then we can get explicit form of the reformation. Then you can directly see what the benefits of our model. That's the motivation.
So the News-Vander problem doesn't have this form, does it?
News-Vander it is, because News-Vander you have the step function, right? Because the demand is
Yes, yes.
above that, you have the piecewise, two pieces. Therefore, satisfy this. Okay, good, thanks. So, right now we know this model is equivalent to the original DRO problem. So I'll focus on this one. So I said, right, in statistics, there is a popular approach, right, to get the efficient approximation is dimensionality reduction technique. Okay, so we want to borrow that idea for this approach. So how, right? Dimensionality reduction technique, that means you use the low dimension vector, right, to represent the high dimension. So the question is how to build that relation, build a good approximation to use the low dimension to represent the high dimension. So we just use the idea of the PCA. So if you use the idea of PCA, that means if you keep that in mind, right? Because lambda, all the consists of the eigenvalues, or they are arranged in decreasing order. So we just keep the first M1 largest, right, eigenvalue. Then we ignore the remaining. Then you have, right, you use the cosine origin is the m dimension. Okay, m dimensional. Right now you use the cosine is the m1 dimension. You ignore, right, the remaining random variables because they associate with the smaller values, with smaller eigenvalues. That means we ignore them. Okay, that's the idea. Then if we can use this, right, low dimension representation for cosine, then we have corresponding approximation. Is right, of course, this is the idea why we consider first M component, right? They call it PCA, just employ, right, linear combination to represent, and the capture in the meantime capture largest variance, and the M1 is the number of principal components. So, right, with PCA approximation, then we can get a corresponding, DRO approximate model, and we denote, right, this optimal value by Z because L means low bound, Z star M1 because M1 is number of components. Then we, in previous result, we established some, the relationship between the, approximation and the true value. So here, why is the true value? Because if you consider this is actually the true value of the origin problem, because here that means you consider all principal components. Of course, you lose nothing. Then, right, because we showed this is approximate, is also is an outer approximate because it provides a low bound. Because this approximate always smaller than true value, is low bound. And also the difference also are bounded by some function directly related to what? Unused eigenvalue. Okay, we established in our previous work, we established this, get a low bound. Also, right, for the unused lambda II, that means eigenvalues. Okay, the smaller, that means this term becomes smaller. That means our approximation becomes better. That's the main result of the first part for the auto approximation. We also call it PCA approximation. Okay, just use the right dimensionality reduction technique. Project the right high dimension to low dimension. Then there's a major two questions to ask. First one is, could we get also get an efficient upper bound? Right? That means can we get an inner approximation for the original problem? Right? This is the first one. And the second one, could we extend the ambiguity we considered to more general ambiguity? That's the two natural questions, right? In the remaining talk, we will answer these two questions. The first, we consider how to get an inner approximation. So, because I want to give the motivation about our inner approximation idea. Because here, you see, actually this is the SDP constraint. If you in the reformulation, right, the problem size is directly because the main factor is decided by this constraint. So our target is to reduce, right, to approximate this constraint. Okay, that's a key idea. So because this is the SDP constraint, then a natural approximation automatically is what? Is we consider, okay, some matrix. Because a big matrix is a PSD. That means all sub matrices, right, are PSD. It's a necessary condition. But all these sub matrices are PSD. The original matrix is not necessarily PSD. So that reason here you consider a bigger ambiguity set. Bigger ambiguity set. That means you will get more cost because you consider more distributions. So this is the if you consider this ambiguity set as to approximate original one, then you will get an auto approximation. Then actually we just do the partition because it's a big matrix, right? You just, for instance, initially you have think about if you have 100 random variables, you can partition by two parts. That means first 50 and the second 50, right? The remaining 51 to 100. Then you have smaller matrix sets, SDP constraints. That's the motivation. So we can with this ambiguity set we can see the approximation set of this LMI linear matrix inequality set is mi plus 1 times m1 plus 1. For instance, if you only do two partitions, that means m1 is a 50. For instance, we consider 100 cases, right? 100 by 100. Here, 50 plus 1 is 51 times by 51. And the two 51 by 51 matrices. But the original one, problem, you can have 101 by 101. Actually, roughly speaking, this size is a half of this. If you do two partitions, the size of SDP constraint become half. That will become more efficient. Of course, if you consider more partition, right, then you will get smaller LMR constraints. Then it becomes more efficient. Of course, this is the trade-off. That means you lose more information. Yeah. So our question is what? What's the the bound? We propose we know this is the inner approximation. How about the bound? The gap, right? So that's the before that, we have this. The main proof technique is use this, because if we consider this ambiguity set, the reformulation technique, the mainly we rely on this decomposition technique. This is the bigger bigger LMI constraint. If all the remaining this part and this part are 0, then you can decompose to the small size of matrix, and the summation of the SI is equal to S. These two are equivalent. So actually, in our reformulating, we just make use of this technique. We decompose, right, n by n original matrix to this a set of smaller SDP constraints. Okay, then right now we answer the question, how about the bound? So that, think about it, right? We denote our optimal value of the inner approximation, right? GU star P. Of course, this is the optimal value of the original problem. It's R bound, right? Greater than P. And also is R bounded by square root P G star. This is the original problem, right? That means, is R bounded by square root P. That means relative, right, gap is the greater than or equal to 0 and R bounded by square root of P minus 1. I want to emphasize P is the number of the partitions. Okay, think about it. If you consider one partition, that means you don't participate. That means you consider the original problem, right? Then here, square root of 1, of course, 1 minus 1 is 0. That means you get an exact form. Clear? Then, second question is around this bound, right? Is this bound tight or not? That means this bound is achievable or not? That's the second question around this bound. Our answer is yes, because we just consider simple case.
So you have two partitions. That's gonna be square root of
2 minus, yeah.
0.7 or
1/4, why?
0.4.
Yeah.
So 0.4.
4, yeah, 40%, right?
40%.
Yeah,
Okay.
relative again, yes.
It's not. So it's kind of high, right?
Yeah, it's kind of high, exactly, yeah, for some case. But most of the cases, that, the R bound is not achievable, right?
Okay.
But of course, some special cases is achievable, we just show later.
There is a worst case where this is achievable, right?
Yes, that's the second question, yeah. This is square root P. That means we cannot reduce this ratio. That's we find a simple example is this DRO problem. We just achieve, the R bound. Original problem is optimal value is square root of m. Okay, if you use we consider P partition, the optimal value becomes square root of P times m. That means the bound is is achievable. You cannot write. That's the worst case. Think about it, right? But later we show, that bound in the most time, right, is not achievable. You make test, right? So right now, then we answer second question before we propose, right? One is how about to get an R bound? We did it, right? The second part is, could we extend, right, more general ambiguity set? We can do is yes, we consider this combined ambiguity set. Do you remember why at the beginning we said there are two popular ambiguities? One is moment based, second type is matrix based. So this, actually, these ambiguities are considered both of them, right? Moment based, the covariance information, and also matrix based, because you have a reference distribution, right? You study that all the distribution, right? The distance to the reference distribution is bounded by R0 part P, and actually this matrix here, the distance is a Bose-Stein matrix. How to define this? Actually, this is the definition about the Bose-Stein matrix. Yeah, and here dp, right, is the distance between cosine and cosine, is the distance between two vectors. Then what's the benefit, right? To consider this combined ambiguity set. I want to talk a little bit about it. For this combined ambiguity set, actually, we take this ambiguity from this paper, not ours, okay, someone else. So I want to talk about a little step by step. For instance, for Bose-Stein ambiguity set, I said, right, in comparison, the KL divergence is either consider all the, even the reference distribution is discrete, but the distribution family also consider continuous distribution. That's the first thing. But also think about it. If a reference distribution, if you have enough, for instance, think about it, if you have infinity samples, then probably your estimated distribution will become exact, right? So, but if you only consider moment-based ambiguity set, unfortunately, if you only consider first and second moment, even you get the exact moment information, but still the ambiguity set is not synchrotron. Is still big. Okay, include the other distributions. So this, roughly, right? What's the ambiguity set? They have good auto sample performance because it accounts for the number of samples you use. Because you have more information, probably you consider smaller radius. Then you have a better solutions. So because directly control the degree of control is just through this, the radius are 0. And also, why we also consider the covariance. Think about it. If your samples are not enough, so you still have some covariant information, then you want to capture that. Then this ambiguity set, is smaller than you only consider what's that ambiguity set. Yeah. But good thing is what? Because here you have this STV constraint, right? Then we can use the same technique we used before for only moment-based, right? We use the auto approximation, we use the PCA approximation. And also we can convert partition of this, right, to get an inner approximation. We can use the same technique to do that. Then, but one more thing, I want to emphasize, if you consider the nominal distribution, just the the empirical distribution, reference distribution, then the number of constraints you can see, right, is decided by the number of samples. Think about it, if you have 100 samples, then you have 100 times k STB constraint. That's not doable. That's very bad. In our later example, we just show even you have 10 samples, you cannot solve the problem directly. That's very bad. So we also have the lower bound. We use the same technique PCA. Then also for the lower bound we have the gap. Also is measured by is directly controlled by unused eigenvalue. Same thing. For the upper bound also is square root of p. The question is for this combined ambiguity set, square root p is also tight or not? But my answer is yes. But I don't give an example. You know why? Think about that. If R0 is positive infinity, then it become what? Then it directly become moment based. Then we use the moment based, we can achieve the type, the bound, right? The bound is achieved. So that reason, here this bound also is tight. It's achievable. So that's we answer two questions, right? One is get a inner approximation outbound, also consider general case ambiguity. The next is a numerical study. So actually, in our working paper, we consider these two main application. One is the research works production transportation application. The second one is a multi-product news-vendor one. And all problems are solved using mosaic. And actually, for the first application, production transportation problem, we just get it from other papers. This is the deterministic version. First, determinism means you have, for example, x, you have m factories and n customers. Then you want here's the normalized product. Capacity normalized. Each capacity is 1. But production capacity. Then you want for each customer, the demand DJ should be satisfied, right? You transfer from the factory I to the customer J, and the cost is cosine ij. Okay, so right, this is a deterministic version. If we have this is when cosine is random, they have this risk averse version because here mu is a disunity function. Then then you have these two stage stochastic risk averse problem. Okay, actually this model we just copy because in our previous paper, we just consider simple C-bar problem. People think, okay, how about more applications? Then we directly copy from some other papers, then to compare numerical compare to numerical to compare the performance. So for example, in their paper also they use this piecewise linear disunity function. With this background, then we have the numerical results. So same, I only show part of the results. So here, in terms of outer approximation, actually PCA approximation, right? We only consider 25% of the principal components, and for the inner approximation, we only consider 4 partitions. Then their result is shown here. Okay, same. If you have for example, for this you have 6 factory and 50 customers, then you use all original exact problem. Unfortunately, it's not doable. But you use this our two proposal approximation. Then this lower bound is upper bound. Because we don't know the true value. Then for this lower bound, actually is what? Is a relative. Okay, here no lower bound the gap. This one is upper bound on the gap. How to calculate this? Actually, do you remember for lower bound, we quantify the difference between the. Do you remember? Still remember, right? For example, for this way, for this lower bound, we quantify the bound on the difference. Then we use this one divided by lower bound value. Of course, is a gap, the upper bound on the gap. Okay, so that reason this is not true gap. That means the gap should be less than this value. And also for the upper bound, the gap, how to calculate? We just use the difference between the two divided by lower bound. Of course, also this is the bound, upper bound on the gap as well. So that means the true gap, should be less than equal to this. Okay, this is for the risk averse production transportation problem, Then this is for the news vendor problem. We have a similar result, For this is very nice, similar like our motivation example, Then original problem not doable, but you provide this, to inner and outer approximation. And same thing. Right now, these are only for the moment-based ambiguity set. Then how about the combined ambiguity set, For the combined one, I want to emphasize a little more, We only consider 10 samples. Well, of course, original problem is not doable. But for our lower bound, the relative gap is big. That means possibly, have some room to, improve that bound. Okay. That's I think the conclusion we can get, This is the relative gap is big, outbound, Of course, the true gap probably less than this, but we know how much it is. And also for the outbound, runoffs become bigger because we only consider 4 partitions and 25%. Same thing, Then we consider another, for the news vendor problem, here is a smaller than the previous risk averse one, and it's faster. So actually we didn't give we didn't show the other result. For instance, we consider more principal components and also the less, right, to show the result. We just use this. I think these two typical examples to show to convey the main conclusion of our proposed approaches. Okay, then also we also apply this technique to some application in power system. For this one actually is the setting problem for the renewable generator for the microgrids. Where to put for the renewable generator, a lot of for the wind, for the solar, right? There's a lot of uncertainty. So we consider DO. For the original problem you cannot solve. Then we take a step back, apply these two approximations in that paper. Okay, then at the end I would like to summarize my talk. Actually, we just proposed two efficient inner and the outer approximation for the DO models. And then second, we also not only we show their inner and outer, but also we develop the bonds with the gap of these two approximations. And the third one is we just I think the more important is our proposed approach, to provide decision makers a flexibility, to deal with uncertainty. That means you can control, if you have more times, of course, you solve the exact problem, or consider more principal components or less number of partitions, That means you have high quantity. If you have less time, or you want to get a solution, faster, that means probably you use the less number of the principal components, Use more partitions. That's a totally decided by decision makers. How do we know? We just propose this kind of flexibility. Then I want to show here's a reference. We use that. Actually, just mainly based on these two papers. The first one is published. This is the auto approximation is published. And the second one actually is a working paper. I think is ready to submit. That's the That's all. Thank you for your attention.
We have some time for questions.
So, can you go to the summary slide?
Sure.
Yeah. So the third bullet. As you change the uncertainty, you can control the trade-off between solution and quality and time. So
you change the answer.
So I guess my question is, were any of the results? Did any of those tables show this trade-off? Because it seemed like that was you're varying the problem size. Is that right?
Yes, problem size, because we don't need a numerical result to show. Actually, we build the gap, so our bound on the gap, the difference between that. We know, for instance, for the first order approximation, we know the more number of the principal, You use the beta approximation we get. But in the meantime, that problem becomes time. You need more time to get a solution. This is a trade-off. Okay. Yeah. Actually, you don't before you implement.
Do you have any results say, if you spend 10 times, the computer time, you get this better bound?
I think that's probably for this type of problem. Probably we can get some information. Is because for some simple one, because the SDB for some simple SDB, the CV is a quadratic increase with number of size. Then actually you can use that kind of information to help you to design already.
In this problem, what's the dimension for K is the number of
the pieces, piece one.
Oh, piece one.
Yeah, piece one, the pieces. Okay, I think I want to emphasize, So if you have number of samples, then that's bad, Then the problem, you have many SDB. So, but people know that theoretically, SDB, problem can be solved in polynomial time, but in practice, that's very bad. For 300 by 300, SDB constraint for our own PC, we cannot solve. So that is one of my main research is either on the DRO or on some other problem. We just focus on how to approximate a SDP problem more efficient. Okay, and also of course with high quantity solution. That's one of the main of my research. Yeah. You can extend more general conic programming.
So, yeah.
Sure.
So the Wasserstein metric is controlled by, your constraint on that is controlled by an R.
Yes.
So if I have a data set and I fit a distribution for my data set, this is F0, right?
Yeah, F0. Yeah, this is a yes.
This is an empirical distribution.
Yeah, empirical distribution.
So how do I choose R? What is an interpretation of this metric? And so what kind of, so if I want to put R0P to any value, what am I saying about the distance between F and F0?
Okay, this is a good question. I think part of our research, our announced research is investigate, right? How to find R0. Because think about it, right? If R0 is big, that means you consider too many distributions, right? Some of them are not true. That makes the problem worse, solution worse, right? If your R0 is too small, of course, you exclude true distribution, right? This is a trade-off. So I think my understanding is that for most of these people do the empirical cross-validation. Use the right in sample part of them numerically, okay. Right? Use for you have 1,000 samples, right? Use 700 and 300 testing to choose the best. That's cross-validation. This is one way. And also, yeah, my thing for the now and some other people investigate how to build, for instance, the probability control. For the R0 is a function of the number of samples, right? It satisfies some condition we can guarantee. So with some probability, it covers true distribution.
So because I do Washington distance,
yeah.
Basically that R0 represents, this Washington distance represents sort of the total transportation cost. Like from your reference distribution, F0 transporting or reshaping as a new distribution. So you're moving the mass probability. What's the total transportation cost? Moving one distribution to the other one, and that R0 is sort of serving as a transportation cost budget. I'm limiting that.
So basically, how much effort do you have to put to transform your original distribution to a new distribution?
Right.
And you want that to be limited by
Yeah.
R0, in
yes.
the sense that the smaller R0, the closer the distribution.
Yes.
Yeah.
So R0 is 0, then just exactly the same
exactly.
distribution. And the thing is, we have some theoretical results on the bound for this R0, how to select this one so that the true distribution can be covered within the Wittgenstein ambiguity set with a high probability.
Okay.
And that one is in terms of or increased by number of size, number of data size, and number of sample size, and number of dimensionality. And that is a sort of a asymptotic like bound. It's not a true bound. And that bound is also, for those bounds I know, theoretical bounds are too conservative.
Okay.
So in practice, the way to select a good value of R0 is cross-validation. So we try out different values and select the best one. All right. Any other more questions? So I have one regarding the computational results. So basically, you select the PCA or PC values with 25% variations.
Yes.
So basically, if you increase, like say to 50% or 75%,
yeah,
like how much your gap can be reduced, or say how much that you can improve your results?
Actually, we just numerically know the more, right? We just can say, roughly speaking, right? The more component you use, the better possibly you get, right? But we don't know, quantitatively, to quantify, so right? You said if you use 50%, right? Then instead of 25% of perceived component, then you use a double number of them. Then, how many percent, right? Percent you can improve. So we don't have that kind of result. We only have the result is bounded, right? Something for the unused eigenvalue.
Okay.
That's
So
the-
like 25% is sort of totally subject to decision maker.
Yeah, this is,
Yes,
they just provide this fact, if you have more time, of course you are using more components.
Okay.
Yeah, because you will clearly write better solution. If not, then probably at least for example, I'm using for the 1 hour, that's my several time, right? I just use 1 hour corresponding to the component to get your solution. Right, just a flexibility. Yeah.
For your object function, lowercase f, you assume it's
Piecewise
piecewise linear maximum of linear functions, right?
Piecewise linear.
So I want, can it be extended to the maximum of concave functions?
Yeah. Actually, you can see the ideal, right? Our proposed version actually is is not is independent of the objective function f(x), right? We can have that, but if you consider more general objective function, then probably we don't have this nice R bounds. But left hand side always hold a bound, but R bound we don't know. Yeah, that's the problem.
So we can reformulate based on your PCA approximation. You can have the reformulation, but you do not have the theoretically upper bound.
Yeah, we can. Yes, if that means if the original problem can be reformulated as some type of problem, our PCA also can same type of problem. We don't change the type of problem because we only do the linear transformation. That means you don't change the type of problem, right? For the only use the linear transformation. So, but if you consider more general, probably you don't have this nice result on the bound. Yeah.
So basically, you mean this upper bound is dependent on the specific form of your object function.
Exactly.
Okay.
But also the reformulation that you provided is also dependent on having the function being a maximum of.
Yes.
The case one, For example, right now we have the SDP reformulation, right? Conic. If the objective function is not piecewise, linear, or something else, then you don't have that kind of reformulation. But my question, if that means that's not my main research. That means how to approximate that kind of, how to reformulate that kind of problem. That's another topic research, right? We just we don't want to change the type of the problem, right? In the meantime, just get a approximation. This idea can be applied to any type of the objective function. Yeah. Because we just
As long as it's convex.
Even not convex, we just do linear combination, right? Whatever,
But if you have a linear combination of the non-convex function, you cannot approximate with linear functions.
No, because we just use the cosine, right? Original cosine, we use linear to approximate the cosine itself. That probably is not convex, probably the reformation that can problem become harder to solve. That's another topic we don't have. Yeah, probably you don't have that kind of reformation. Yeah.
So basically, if I understand your answer right, so basically you said if your original problem can be approximated, then the reformulation must be okay. If your original problem cannot be approximated, then your reformulation does not have this power to approximate.
Exactly. Yeah. That's it. Okay.
Okay, let's thank our speaker again.
Okay, thank you.
And we're going to launch a
Sure. Where are you guys going?
Excellent.
Okay.
Wait, a little funny.
Yeah, I need to send out an email, and so I'll join you there.
Sure, yeah.
Before.
Yeah,
So I'll just meet you there.